The piston engine is a heat engine. Its purpose is to convert the heat energy released by the fuel into mechanical energy, and so allow it to do useful work. In the engine's general lesson, we stated that the thermal efficiency of a piston engine is at best only 25 to 28%. This means that over 70% of the heat energy released by the fuel in the engine is wasted. The exhaust gas is responsible for releasing around 40% of the heat energy. On some aircraft, some of this energy can be recovered by using it to drive a turbine-driven supercharger, which is commonly called a turbocharger. The remaining 32% of the heat energy released through burning the fuel raises the temperature of both the engine components and the oil. If this temperature increase is not controlled, it could be the cause of several problems. For instance, the oil temperature becoming too high, which would cause it to lose its lubricating properties, and, as a consequence, the engine would suffer possible structural failure of some of the components. Also, if the engine gets excessively hot, carbon deposits in the cylinder can become incandescent. The hot spots thus created can cause the mixture to ignite before the normal ignition point. This process is called pre-ignition. The combustion process can even become unstable after the mixture has been ignited at the normal point. This is called detonation or knocking. Both pre-ignition and detonation result in a loss of engine power. So far, only the problems of overheating have been discussed, but problems can also occur if the engine operates at too low a temperature. We must always remember that for two reasons, in order to obtain high values of thermal efficiency, it's required that we operate the engine at high temperatures. Firstly, low engine temperatures increase the internal friction of lubricants. It increases the viscosity of the oil. This would increase the friction horsepower within the engine, and thus reduce the brake horsepower available at the propeller. Secondly, the ability of the liquid fuel to change its state from a liquid to a vapor is reduced in a cold engine. This affects both the fuel mixture strength from cylinder to cylinder and the ability of the fuel to burn efficiently. Bearing these two factors in mind, then, it appears that to operate efficiently, the engine must operate at the highest temperature consistent with safe operation. Inevitable fluctuations in the ambient and engine internal temperatures require a cooling system to control and maintain the engine temperature at the optimum level. We examined the way in which the cylinder arrangement differed between engine types in the engine's general lesson. We said there that the cylinder arrangement was dependent on the power required from the engine and the type of cooling system which was used in the engine. The two types of cooling system used in aircraft piston engines are liquid cooling and air cooling. The liquid cooling system shown in this diagram dissipates the heat generated in the engine by pumping a liquid through passages built into the cylinders and cylinder heads. This liquid, which can be a mixture of water and antifreeze, is then passed through a radiator which is mounted in the slipstream of the propeller. This placement ensures that, even with the aircraft stationary on the ground, there is a flow of cooling air through the radiator. To enable both the size of the radiator, and therefore the amount of drag it generates, to be reduced, some engine manufacturers employ liquids which have a boiling point appreciably higher than that of water. One such liquid is ethylene glycol, a molecule of which is shown here. It's a clear, rather viscous liquid. When mixed with water in a 1:3 ratio, ethylene glycol raises the boiling point of the coolant, thereby preventing low-pressure boiling at altitude. It also provides good antifreeze properties. The use of this liquid can enable a reduction of radiator area of up to 50% in certain engines, like the Rolls-Royce Merlin or Griffon engine, which can be mounted in the Spitfire. The components of the liquid cooling system consist of an engine-driven pump, which circulates the liquid through the engine, a thermostat which controls the coolant temperature, a header tank which acts as a reservoir for the coolant liquid, pipes to allow the liquid to flow from the header tank to the engine block, and then from the engine to the radiator and back to the header tank. Air flowing through the radiator dissipates the heat from the coolant to the air. The standard design of air-cooled engine uses the cooling air from the propeller slipstream and the forward speed of the aircraft to transfer the heat generated in the engine directly to the air. The engine is surrounded by cowlings which reduce drag and control the flow of air around the engine. The controlled flow ensures that all parts of the engine are equally cooled, and it thus prevents overcooling of the front of the engine. The cooling system of the air-cooled engine has few moving parts, and thus the simplicity of the system makes it virtually maintenance-free. An air-cooled engine is also lighter in weight than a liquid-cooled engine of similar power. These are the two main reasons why an air-type cooling system is preferred on gasoline-powered aircraft piston engines. Nevertheless, it should be appreciated that a liquid cooling system is more efficient than an air cooling system. Liquid cooling gives better control of engine temperature and also produces less drag. To assist you in comparing the frontal area of these two types of engine, we have superimposed a representative liquid-cooled engine type over a representative air-cooled engine type. Both engines have similar power outputs. It is for these reasons that liquid cooling systems are used on the very powerful engines of high-speed aircraft. The main factors governing the efficiency of an air-cooled system are, firstly, the ambient air temperature, which can vary widely with changes in climatic conditions and altitude. Dissipation of the heat generated in the engine will be more rapid as the air temperature decreases. Secondly, the speed of the airflow passing over the cylinders, which is governed by the slipstream, and thus will vary with the speed of the aircraft. Some engine installations require that care be taken when ground running to prevent overheating, because as the aircraft is stationary, the only airflow over the engine comes from the propeller slipstream. On the type of installation where this is a problem, a fan may be fitted behind the propeller to obtain a greater airflow over the engine, as is shown in this diagram. The external surfaces of the air-cooled cylinder and the cylinder head are finned to increase the cooling area. The engine designer walks a fine line between ensuring that the pitch of the fins is such that a large fin area can be obtained, whilst ensuring that the fins are not so close that the resistance to airflow builds up pressure, which would tend to decrease the airflow and thus increase the drag. An average pitch for fins on a steel cylinder is about 4 per inch, whereas for fins machined from cast aluminium alloy, the pitch is less than 3 per inch. The fins have a thin cross-section. They may be extended at local hotspots so that their surface area increases, in an attempt to produce an even temperature throughout the component, for example around the exhaust ports on the cylinder head. Baffles, which are shown here on this diagram, are air guides, which direct the airflow completely around the cylinder. They must be close-fitting and provide a seal with the inside of the cowlings, so that all the cooling airflow is directed around the cylinders. Care is taken to ensure that an even cross-sectional area is maintained, so that the airflow does not slow down and cause drag. Cowlings must be close-fitting without dents or projections which may disturb the airflow over them. Any disturbance to the designed airflow will not only increase the drag, but also decrease the cooling effect it delivers. Cowl flaps, or gills as they are sometimes called, when they are fitted to an engine like the one depicted here, are fitted to enable control of the airflow through the engine. With the cowl flaps or gills open, the air flowing over the engine cowling causes a pressure drop at the cooling air outlet, thus accelerating the heated airflow and enabling it to maintain a high speed over the cylinders. As the air flows over the cylinders, it absorbs heat and expands. This increases its speed even more. Any increase in the speed of the air mass flow through the engine creates a reactive force, which, by acting forwards, tends to negate some of the total engine drag.